Applications of linear functions, which again, I'm scrapping that word and I'm using equations. So the key to this is that we're going to try and take some word problems that are probably not very realistic. Most of our word problems haven't been very realistic, right? But the whole idea is that you have some situation in the real world that you're going to try and model with a linear equation. And then we can do all the stuff we've done with a linear equation. Find the x-intercepts, y-intercepts, slope, all that. And that now it's going to have meaning to us. So let's just take a look at, I'm going to look at number 1 here. It's about Mr. Thompson is on a diet. All right? Mr. Thompson currently weighs 260 pounds. He loses 4 pounds per month. £4 a month. Write a linear model that represents Mr. Thompson's weight after M months. So the idea is this. You want to come up with some equation that's going to model what's happening to his weight. Right? So it's going to be your x and y axes, but we're only going to be looking at the right side of it because this right here, instead of using the variable x, we're going to use variable m because it says m months in there. And this is going to be the number of months. And then the y-axis is now going to be what? His weight, right? So, and it's measured in what? Pounds. So the question is, how much would he weigh at 0 months? 260, right? So I could come up here and I could mark out here 260, and I know that that point represents where he started, what his weight was when he started. And then every month, right, after 1 month, it's going to drop down to what? To what? He's losing 4 pounds per month, so 256 after 1 month? So he'd be down here, let's say this is like 256 right here. And then after the second month, he loses another 4 pounds, right? So he would be at what? 252. And what we have here is the assumption that the weight loss is linear, meaning every month it's always 4 pounds, 4 pounds, 4 pounds, 4 pounds, right? The assumption here is that we are going to model this using a line. So we could connect these together. And eventually, if he does this long enough, according to our model, eventually he will no longer exist, right? But that's why a linear model is not a good model for weight loss, but it's a starting point, right? We can get a basic idea of what's going on. Okay, so what we want is a linear equation that models this. So you can see the line. What do we already know? What is this on if we were to imagine that our line went forever in each direction, what is this point on a line? Our y-intercept, isn't it? So in terms of an equation, we know what the y-intercept is. Let me try and come up. So we want an equation, I should put here linear. Relating his weight, which we will call W, to the number of months, which we will call M. So his weight should be equal to what? 260 is what he starts at. And then what? Minus 4M. So what we're going to do is we're going to take away 4 for every month. So isn't the negative 4 this slope? Down 4 over 1. Down 4 over 1. Down 4 over 1. Down 4 over 1. Now it's not drawn to scale. Do y'all know what I mean by that? Like 1 unit this way is not equal to 1 unit that way. That's okay. We do that a lot just to make it all fit on one picture. Or to fit easily onto our paper. So this slope is equal to negative 4. And the y-intercept is 260. So you can write it this way, or you can write it more like we did with our y equals mx plus b. That would look like more like y equals mx plus b, doesn't it? Y is the w, equals m negative 4 times x, but x is m plus 260. Good? No questions? Okay, that's our model. This is our model right here. Now let's look at part B. After how many months will Mr. Thompson reach his goal weight of 220 pounds? After how many months? So how many months until Mr. T is how much? 220? Well, we have our model, right? We have our model here. We're looking for months, right? The time measured in months. That's what we want to know. And we want to know what that value is, which makes his weight, what? 220. So all I have to do is use this equation right now, replace W with 220, and then write the equation. So 220 equals negative 4m plus 260. Now you probably could have counted, like minus 4, and counted how many months, but this is a more efficient way because we can do this for any weight. And so solve this linear equation. We're trying to solve an equation. There's only one variable in it. Isolate the variable, right? So start moving things around. How about subtracting 260 from both sides? Sound good to you? Yes? So subtract 260. This will give me negative 40 equals negative 4m. And divide both sides by negative 4 and we have 10. Does everyone understand the importance of doing this? And that, like on a test or on a problem that's maybe not so clear, it's obvious he lost 40 pounds, right? 4 months a pound, or 4 pounds a month, 10 months. We could probably do that mentally, but we need a way that we can do it if it's not so easy. Agreed? Okay. I should have, I probably have it on my laptop, but I don't think I'll show it. Every once in a while, I'll like train for a triathlon or something, and I always have to drop weight for it. And this is exactly what I do. I have a model of a linear model that I use to figure out how long it's going to take me to get to my like competing weight. And so I can tell you right now that when I train really hard, my slope, my M here is about negative 0.321. I know that seems crazy, but that's per week. So I lose about a third of, no, hold on. That's a day, sorry. So when I'm really training hard, I can drop a third of a pound a day, about, and still stay healthy and not, go crazy, not die, exactly. But that's like the max of what you should ever do. You should never try and drop weight any faster than that. But per day, yeah, like a third of a pound a day. Yeah. But then I plateau out. I get to a point where, yeah, I don't just wither away into nothing. So, all right. Well, how about a bacteria problem? A bacteria population doubles every minute. Doubles every minute. Explain why this population growth cannot be modeled using a linear equation. Why it cannot. Okay, What's that?
I mean, well, it won't make a line.
It won't make a line. So let's see why it won't make a line. All right, let's see. If you let's start with one bacteria. Okay, let's say here's one bacteria. I'm even going to put a little smiley face on him because he's a happy bacteria. All right, there he is. You start with one. After 1 minute, okay, after 1 minute, how many are there? It's doubled, right? I'm going to stop drawing the smiley faces. Okay, so this is 0 minutes. I'm going to make almost like a little table here. This is 1 minute. Okay, how many should be there after 2 minutes? 4. But what's happening here is that one's split into 2, right? And now the next one's going to split into 2. This one's also going to split into 2, so you're going to have 4 after 2 minutes, right? So if I were drawing this right now, okay, if I were to draw this and this were minutes and this were the number of bacteria, look at what this picture looks like. At 0 minutes, how many do we have? 1. After 1 minute, how many do we have? 2. After 2 minutes, we have 4. Y'all okay with that? Does that look like a line? I'm a little off here. Does that look like a straight line to you? Let's try the next one. How many would I have after 3 minutes? Careful here. How many? 8, not 6, right? We have 2 from here, 2 from here, 2 from here. See, each bacteria doubles after 1 minute. So now you're going to have 8 of these guys. So if I come out here to 3, I'm way up here at 8, right? And do you all see that that's not a line? I mean, can you tell that I can't connect these with the straight line? And so this is not linear growth. This is what we call exponential growth. So the whole point of this problem is just to let you know that not everything can be modeled with a line. Bacterial growth is one example. All right, let's do another one. Tuition. Let's do tuition at college. So there's a college called XYZ, and it is $100 per credit hour. And an additional $75 student fee. It's a pretty cheap college. Can we model this with a linear equation? Well, let me finish this. What is the one-time charge or fixed cost? So the student fee, right? No matter what, if you take 12 hours, 9 hours, 6 hours, doesn't matter, you have to pay the $75 student fee. So our fixed cost is $75. All right, the next question. What is his variable cost? Who's his? I don't see any reference to a guy anywhere. Okay, what is the variable cost? So what matters? What's affecting the cost of tuition? I mean, what changes? What's variable here? Yeah, how many credit hours, right? So the variable cost is the credit hour cost, right? And then write a function t of x. So this is the first time we've seen this notation before. The tuition, and then parentheses x. What this is saying is we are going to say that the tuition depends on x, is a function of x. And x is going to be the credit hours. Let's not do cost. Let's just call this credit hours, x. That changes, right? How many hours you take? So tell me about this cost. Definitely, no matter what, it has to be what? If you're going to go to school there, no matter how many hours, got your fixed, right? 75 plus, because you have to pay something in addition to that, what? $100 per credit hour, and if X is the number of credit hours you're going to take, then it's going to be 100X. So if you take 1 credit hour, you're going to pay $175, right? 2 credit hours, 200 plus 75, 275. And that is a linear equation. Now, if we scrap this little notation here, we could just write, tuition equals 75 plus 100x, and it would be the same thing. We would have x being here, we would have t being here, and then we'd graph our line. What would the y-intercept of that line be? 75. And we'd have a slope of 100, right? So it'd be a positive slope, not the guy losing weight, right? It would be this. So the more credit hours you take, the more expensive it's going to be. Okay. Let's move on to I think 5 looks pretty good. Does everyone who has their stuff with them on number 5 have Joe and a part-time job walking a dog? Okay. Okay, so I'm looking at the one that's Joe has a part-time job caring for and walking dogs. All right. Someone's got to do it, I guess. He estimates his annual insurance and costs at $420. Annual costs at $420. What is that looking like it's going to be in the problem? Like, compared to the last problem, what is that kind of going to be like? The fixed cost, right? The $75 student fee? Like every year he's going to have to do that. Like for whatever reason, he's going to have to pay $420. On average, he spends $4.50 on gasoline per visit. I guess a visit meaning he's going to go take care of a dog or some dogs. He charges $15 per visit. It says, note that this is an annual cost function. Part A, what is the one-time annual charge or fixed cost? We already said, right? The 420? B, what is his variable cost? These both, right? These are both part of the variable cost. Because every visit he makes, he's going to pay so much in gas, and every visit he makes, he's going to have a charge, right? But these work against each other, right? Like this is income, this is out, right? So let's actually label this thing as a variable. Can we call it, I think they want us to use X. X is going to be the number of visits. Isn't that the thing that's going to control his cost? How many visits he actually makes is going to be the variable here. And then finally, we can write a cost function. And they want you to write it C of X. Let's see if we can do it. What's the fixed cost? 420, so we can put that out here. Plus, now, how do you want to do this? You can do this different ways, but let's see how. Anyone have an idea of how they want to incorporate?
Minus 4.5x?
15x, so 15x, you want me to put plus 15x, because that's going to be money coming in, coming out. See, we have to be a little careful here. We want this to be a cost function, right? Cost. How much cost does he have? So is this 420 Income or out? Expense or it's out, right? No matter what, he's in the hole 420 per year. So we should incorporate this 420 in our equation as a negative because it's a cost, right? So let's go negative here, 420. And then the 15 is income or expense? It's income, right? Money coming in, so it's a plus. And then what about the 450 in gas? It's going out, so minus 450 per visit, so times X. And now we can actually put these together, right? Because they're like terms. So what's 15x take away 450x? What is it? Plus 1050x. Does that look like a linear equation? Does that look like your y equals mx plus b? Yeah? If I graphed it, the y-intercept is what? Negative 420. And then your slope is positive, isn't it? 1050? So it's going to go up like this. Agreed? What is the importance of this point right there? What is the importance of that point? That's actually called the break-even point. It is the break-even point. So if he's going to run his business, he's going to be out 420 no matter what. So he's got to do some work or else he's out, right? How much work does he have to do just to break even, just to offset the 420? Well, that's going to be, right, this is x. This x-intercept tells you where his cost is 0. Where is that? So this is your cost, right? If I were to say C equals 10.50x minus 420 like that, if I were to ask you to find where he breaks even, I'm asking you for the x-intercept, right? So to find x-intercepts, you set y to 0, but we don't have y, right? We have c instead. So all I'd have to do is set c equal to 0. I realize this question I'm asking you is not in here, but I'm just trying to see if you can make the connection. If you set c to 0, then you get this. If c equals 0, turns into 0 equals 1050x minus 420. You move the 420 to the other side, and you divide now by 1050. So someone please on their calculator.
840.
What is it, 840? So how do I interpret that? This is my little dog walking business. I'm going to have to do how many visits to break even?
It's 40.
Oh,
Sorry.
it's 40. Okay. Yeah, that seemed a little off. 40 even? Oh, okay. Well, going to have to do 40 visits, 40 dog walks a year. It's 52 weeks in a year, 1 a week. I don't know how busy this guy is, so maybe it works out for him. Okay. Do you think you can handle some of this? You're going to have to just go through the homework on your own and see how the problems look. Okay, let's talk about a different type of problem. These are called mixture problems. So we're stepping away from that for a minute. All right, I'm going to look at number 1. If there is a mixture of 7 liters of water and 17 milliliters of ink, write in decimal form how many total liters there are of this mixture. How many total liters? So what do you have to do? Convert what? Milliliters to liters, right? Let's convert this milliliters to liters. Because what we're doing is we're taking 7 liters of water, we're adding 17 milliliters of ink, and we're mixing it up, right? And we have some ink solution there. How many liters are there? So first, 17 milliliters, we did this on the test, over 1. What's the conversion to go from milliliters to liters? Give me any relationship between them. 1,000 milliliters equals 1 liter, right? That's our relationship. So I'm going to use this equation. I'm going to write my fraction out here. What goes on top? Liters, 1 liter. Bottom, 1,000 milliliters, right? So this turns into what? .017 liters. That's how much ink you have, right? Add it to the water. Yeah? So your mixture is the 7 liters plus the .017 liters, which of course is just 7.017 liters. Okay, let's do number 2 here. If there is a mixture of 2 liters, did anyone have a question on that? All right. If there is a mixture of 2 liters of 10% butterfat milk, okay, and 1 liter of 0% butterfat milk, also called skim. How many liters? And we're going to mix these together, okay? We're going to take these two, we're going to mix them together. The question is, how many liters result, and what is the percentage of butterfat in that mix? There's all sorts of different ways to do this. All right, so let's see if we can come up with a way that makes most sense. Two liters, right? It's 10% butterfat milk. That means 10% of it is butterfat, I guess? Yes? So how much of this is butterfat? Only 10%, which is a small amount, let's say. If we were able to separate the butterfat from everything else, 10% of it would be butterfat, the rest would be the rest, right? So how much is that in there? How many liters of it? What's the computation you have to do to figure that out? What's that? 10. Yeah, convert this to a decimal, 0.1, right? 0.10 times 2. So you're saying 10% of 2 liters is what? 0.2. So this is 0.2 liters of butterfat. I'm just going to put butterfat, right? Does that make sense to you all? If you got 2 liters of stuff and they're saying 10% of it is butterfat, then that means 0.2 liters of it must be the butterfat. The rest of it is just water or whatever else. We're going to take that and we're going to mix it together with another mixture over here that's just 1 liter, and it has how much butterfat in it? 0 butterfat. When I mix those together, how much do I have total? How many liters will I have total? 3 liters, right? I'm going to have 3 liters. So I mix them together now. I have 3 liters now. How much of it is butterfat? Still 0.2, right? We still have down here, that 0.2 had to come with me, so we still have down here 0.2 liters. So the question being asked here, there's 2 questions. How many liters result? So what's the answer to that question? 3 liters, we're done. What is the percentage of butterfat though? What's the percentage? It was 10% here, right? But here, the question you're asking is 0.2 liters is what percent of 3 liters? 0.2 liters is what percent of 3 liters? And you convert that into an equation, which would be 0.2 is equals what percent is x times 3. That's what I asked you to do on the last test, right? Something like that. And we're solving for x. All you do is divide both sides by 3. What do you get? 0.06. Close enough? 0.666? Ooh. Okay, repeating equals x, which means, convert that to a percentage, 2 places to the right, 6.6 percent, right? Approximately 6.6%. I want you to try the next one. I'll put it up here on the board and give you a little bit of time. You have a mixture is 2 liters of 11% saline, which is salt, and 3 liters 3.1 liters of water. Mix them together, okay? Mix them. First question, how many liters? Result. What is salinity? Percentage. How much salt is there as a percentage? If you have it, raise your hand. If you have both of them. Okay. Let me see what you're getting over here, Sean. So 5.1, and then you divided. So did you do this and this together? Right? The question, you got to figure out how much salt is there to start. This is just like the problem we did before. So 0.22 liters. What are you doing here? I'm trying to, okay, that, I got you. And then you divide through, okay, got you. Whenever you're working with an equation like that, you just like work straight down. Because if you look at it this way, you're saying that this equals this. Okay, but you got it. Anyone else getting it? Yeah? What are you getting for your salinity percentage? Around what? 4.3? Oh, 4.3. I think, how many liters did you have total? I think you didn't take that into account. When you put these together, it's 5.1.
Oh.
Not 3.1. Yeah, sorry, I didn't catch that the first time. 0.43. Then convert that to a percentage. 4.3. It's looking like 4.3%. Did you get 4.3?
I calculated it out. I know what I have to do. I just don't have my calculator out. It's just 2.22 divided by 5.1.
Yes. Okay. All right. So how are you doing here? Okay, good. You get your amount of salt, and you're going to get this result. Yep. And then you take that and set up your equation. It should be this number divided by that. Okay. Did y'all get it? So how much salt was there? To start, how much salt was in here? Okay, it's 11% of 2. So you have to do 0.11 times 2 first. That's how much salt is there to start. Are you following that, or? And then you take that and divide it by the 5.1 that you get when you mix them. You got 4.3-ish percent? Okay. Yes, no, yes? 5.1, yeah. Because you're adding the two together. So now you have 5.1 liters, not 3. Did you round? Let me see what you're... Did you do 0.22 divided by 5.1?
Oh, that's what I forgot. The 0.1.
0.1, there you go. Okay, I think mostly everyone is there, can probably finish it off. Look, the theme of the two problems I just showed you is that you have a certain container with a certain amount of stuff in it, salt, butterfat, milk, and you're going to mix it with some other container that has however much of it is. It's been 0 the last 2 times, right? It's nothing in here. You want to mix them together. When you add these two together, you're going to get a total container now. It's going to be those two amounts added together, right? So 2 and 3.1 is 5.1. But the question is, how much of it is still the salt or the buttermilk? Well, you have to figure out how many liters that is. How many liters of this salt there is. And to do that, don't forget the step. You have to take 11% of 2 to figure out how many liters there are. You can't say 0.11 liters. That's not how much there is. It's 0.11 times 2. If this was, 15, then it would be 0.11 times 15. That's how much salt is there. Now, the reason why it's important for us to understand this is because of the next question. All right. I'm going to look at number 5. It's saying something like, how much water is required to be added to 1 quart of 3% milk to result in a 2% solution? So this is very different than what we just did. All right, I've got some milk. All right, I've got 1 quart of 3% milk. Now let me draw a picture of what this means. I've got 1 quart and 3% of it is milk. So if I could, it's water and milk mixed together, all right? So if I look at it, it's actually only part of it is milk, right? 3% of this is milk. How many quarts of milk are in there then? How many quarts of milk? I have 1 quart of everything. How many quarts of milk are in here? You're going 0.03 times 1 quart, right? Understand that? So you do 0.03 times 1 quart and that tells you you have 0.03 quarts of milk. Okay, so that's what I'm starting with. I've got this 1 quart of 3% milk. They want me to come over here and mix that with something else, right? With water. And at the end, I want to have a 2% milk solution. How much water do I pour in? Mix with it. Do y'all see the difference between that and the previous one? The previous one, they told you, hey, take these two and mix them. What's the result? Now they're telling us, take this one, mix it with water, and they're telling us about what they want the result to be. So I'm supposed to come in here and add something to this, right? I have some container here of water, which means you have how much milk? 0% milk. And I don't know how much there is of this. I don't know how many quarts there are. I don't know. That's the question. I need to add those two together. And what do I want my result to be? Just 2% milk. This is tricky. It's a lot different than the last one, right? So when I add those together, I'm going to get a result, and let me put my result over here. The result of adding these two together should be some mixture, and it's 2% milk. Okay. Everyone understand the problem? Yes? No? What do they want? What are they asking for? They want that, yes, but what is it you have to actually solve for? How much water you're going to mix with this, right? That's the question. How much water do I have to mix with this to get a 2% solution out? So I'm going to write that down. How much water in quarts? Why am I in quarts? Well, because that's what they started with, right? Quarts. Do I need to get a 2% milk mixture? Well, since we want to know how much water, why don't we call this thing something? And we don't know what it is, so why don't we use a variable? X, W for water, it doesn't matter. But we've used X a lot, right? So how about X? We're going to call this X. So I'm going to come in here with this 3% milk solution, 1 quart of it. I'm going to put it in this big old bucket, all right? Then I'm going to come and I'm going to pour in how much? I'm going to pour in X and mix those up, and at the end I need 2%, right? Okay, we're kind of reversing what we just did. So if I were to actually ask you right now how many quarts of water you're going to add, you would tell me what? X quarts, right? X quarts? X quarts of water? Agreed? How many total quarts are you going to have when you add these two together? Whatever X is plus 1. Agreed? So your mixture, I'm running out of room here. I'll leave this. This was 0.03 quarts of milk. Okay, when I add them, the mixture, I will have X plus 1 quarts. Yes? How much milk will be in there? How much milk? 0.03. You can't, look, you're adding water to this, right? You can't make more milk appear. So you are fixed. You've got a mixture, it's X plus 1 quarts, and it's 0.03 quarts of milk. You still with me? So in my drawing of my picture, I've got this thing, I know that I've got a fixed 0.03, but now this is actually x plus 1 quarts. In the problem you just did, wasn't it 5.1 when you mixed the two? Right? 5.1 liters. Here we don't know what that is. But what do we know about this mixture? At the end of the day, it must turn out to be what? 2%. Which means when I take this amount and what did we just do? Look at what you just did. You did 0.22, right? Divided by 5.1. What was the 0.22? How much salt you had, right? And you divided it by the 5.1, which was the total amount of liquid. And that gave you the end result, the end concentration. What we know here is we know how much milk is there. We don't know how much stuff is there, but we know that the ratio has to turn out to be 0.02, 2%. So that is the equation I'm now going to set up. I know that the amount of milk total in the mixture over the total amount of liquid must be equal to 0.02. Do you agree with that? This is a harder problem, right, than previous ones? And now what we do is we try and solve this for x. That's an equation, right? Just has x in it? All right, so let's try and solve this for x. So if you did your homework, there was some problems where you had x appear in the denominator like this. You could write this as a fraction. And how could I get x plus 1 out of the denominator there? Multiply both sides by x plus 1. So let me try this. I'm going to write it over here so I have a little more room. So I'm going to multiply both sides of this equation by x plus 1, by the entire denominator. And what I do there, I must do here. And that will have the effect of making the left side cancel out like this, right? Do you follow? And on the right side, I will have to distribute, won't I? Because this is just 0.02, it's going to have to distribute through this parenthesis. So what is still on the left side? 0.03, that's it. Equals, over here, first multiplication, 0.02 times x, 0.02x, 0.02 times 1, plus 0.02. Now you have a nice linear equation with just one variable in it. You can subtract 0.02 on both sides. When you do that, you get .01 equals 0.02x. And if you divide that, you should get 0.5. So let's see if we can now interpret that answer. What does that represent? What is that? 0.5 what? That's how many quarts of water we're going to add, right? So 1/2, 0.5 quarts of water. So I'll kind of back up a little bit. We had 1 quart of 3% milk. We figured out that if you take half a quart of water and you add it and you mix it up, you will have a 2% solution. How much will you have? How much of it will there be? 1.5 quarts, right? You started with the 1 quart, you added half a quart of water, so now you have a 1.5 quart mixture, but it's 2% milk instead of 3%. This is the way, this is like the basic stuff they do in chemistry classes. Like if anyone ever taken a chemistry class? No, not yet? In a chemistry lab, they'll have solutions that they use in chemistry. where they'll have like some acid or something, and they have like a storeroom in the back where they keep everything. They'll have like a 10%, then they'll have maybe like a 30% solution, and then maybe back there they have like, I don't know, a 60% solution. And what they'll need to do is, for the experiment they're running, they'll need to make a solution that's 22% acidic. Well, they don't have 22%. They only have 10, 30, and 60, so they don't say, oh, well, never mind, we can't do it. They have to figure out how much of this one to mix with this one to make it 22%. And that's beyond what we just did right now. It's a harder problem, but it's leading up to that same idea, that you can actually figure these things out. And that way you only have to store these in the back, right? You don't have to have all these special ones. You can just have basic big vats of these and just use them as needed. All right, I think that's a good break point. You want to take a little break? All right. It's kind of good we didn't put this stuff on the test, right? Because you would have had a test on it the next day. That would have been kind of tough, huh? Yeah, they should be able to. I hope they can. There's never any guarantees.
Do you teach
Pre-cal?
calculus 1?
I haven't taught pre-cal in a long time. I teach the 1414 course, which is the other one, college algebra, and I usually teach Cal 1, Cal 2, and Cal 3. For some reason, I just haven't taught pre-cal in a while.
Gotcha.
Yeah.
So I think I'm going to have to take it in the fall. Well,
You are?
Well, maybe. I might.
What about the 1414?
That's what I was going to kind of want to take.
Are you changing your major or something, or?
Well, my major's civil engineering. I'm just kind of taking some basics right now.
So why did they put you in here?
Oh, because I needed this. I just needed this class because it didn't count in high school, and so I have to retake it.
Yeah, but you have to take 1414. This is 1314.
I wasn't ready for 1414.
Okay, that's fine.
Yeah.
Yeah, that's
So-
good. Okay, so that's probably a good thing to kind of get yourself going again.
That's exactly what I need to do.
1414 is going to be like, boom.
Yeah, that's
wake
kind of what
up.
especially doing the flex course. I signed up for it, and then the first day, because I was also taking English too at the same time.
Okay.
And he was like, all right, do this homework. I think it might have been you. I'm not sure. Maybe not.
Maybe.
Summer 1.
No, not summer
Okay.
one. No.
But he was like, all right, here's the homework. You can't do it. You're in the wrong class. I looked at it and I was like, oh,
Yeah.
crap.
Yeah.
But here, I mean, everything's kind of
Okay.
familiar.
Okay.
And so I kind of want to jump into 1414 maybe in the fall. I wasn't sure because the way you explain things is really helpful for me, and that'd be awesome to kind of keep the motion going.
Yeah, I'm not doing a 1414 in the fall. I do have videos that I did for 1414, but I mean, they're not really designed for like people to go and watch to like learn it. It's more for like my class that semester just to have a reference. But yeah, man, have you registered? You haven't registered, right, for fall? Okay, if you can tell me like what instructors you're looking at, I can kind of give you some opinions.
I am
You know.
doing fall. No, I'm doing
Thank you.
fall, and then,
Yeah, no problem.
hopefully, if everything works out.
Oh shit. Hold on a second. Well, okay.
Nothing. I didn't really do anything bad. It was like my room. Just like My notes, I don't really keep good notes on this stuff, like it'll be like everywhere. I gotta keep. I'm gonna start using the videos. Same. And
No, let's not do it that way.
oh yeah, my next exam, I'm really trying to get yeah, I got, I worked at home, but I got work from home. I'm pretty confident about I'm not really sure how.
That's not really like.
You do not have to write all of this down if you want to. I'm putting this up here for a reason to show you how ugly this definition can be. If you want to, you can. For all x value, all x value for which.
First thing we had to memorize the definition of a function.
Mm-hmm.
All
x values for which definition.
Oh, it's also on your test. If you open up the second page. I'm good with like work and stuff. Homework, I was like doing it Saturday and I never said something.
Honestly, I did that. I'm gonna try like taking the problem all of
I'm just trying to, I'm not using
Oh, yeah.
I figured that if I just studied for a year, I would find, because if I would have gotten a thing if I would have it was like, I got like an 81 and
I just, I probably, if I do use one, I get an SAIST because it's formula heavy test.
like this one.
This one, might, yeah.
I'm gonna try not to get I've learned my lesson.
You've got about one more minute. Is everyone back? Wait, I think everyone's back. Oh, John Paul's not back. Who, did anybody come in that didn't get their test? Anyone not pick up their test? Okay. What is that?
Oh, got it.
Can you what?
Are we getting into this now?
I doubt as rigorous as that, but yeah, no. I'd have to see how in depth that goes. I don't think so. Maybe a little bit later. I mean, we will talk about quadratic functions and parabolas and stuff, but it will not be the same. Let's see, sign in for Wednesday. So it should be this column right here. Sign in for today, please. Okay, let's go ahead and get started. This is going to be a very brief section. We're going to talk about functions and functional notation or function notation. So I put up here the kind of a precise definition of a function, but I didn't put it up here with you wanting to necessarily copy it. I wanted you to see how ugly this thing can look. You know, a function is a rule which assigns to each element x a single value called f of x. All x values for which this function is defined is called the domain of f, and all the values of the function is called the range of f. And if you just look at that, it just looks like gibberish to most people. So I'm going to do something instead of the definition. I'm just going to draw pictures because, I don't know, people like pictures, I think. Okay, a function is a machine, okay, like a car wash. Right? You take your car to the car wash, the ones that you drive through, you know, you go in, dirty car, comes out clean car, if it's a decent car wash. So a function is the same way. You have something you put into the function, which we call the input, goes in through the machine. The machine here is usually labeled f, and you have some output. The things that we normally plug into the machines in this class, into our functions, are numbers. Okay, so the input we're going to use are numbers. And the output of our machines are actually numbers also. So you take a number, you do something to it, and then you spit it out, and it's usually changed. It's usually it's not what it was when it went in. Now sometimes you plug it in, it comes out unchanged, and that's a very special function. It's called the identity, but we can get to that later. So input is a number, output is a number. The notation we use for this is the input, we use the variable x. In the output, we write f with parentheses around an x, and we say this, we speak this, we say f of x. That's how we read that, f of x. So x is the input. What comes out of the function, the output, is f of x. So please understand that f of x is the value coming out of the function when x is plugged in, right? If you change the x, the output's going to change. So I'll start this out with an example that we've all seen, y equals 3x plus 1. This is a linear equation, right, with two variables in it. And we already know that that's a line, y equals mx plus b. And if I start changing the values of x, it's going to force the y value to change, right? So you could say that y depends on x. Every time you change x, y is going to change, so y depends on x in order to determine its value. So I can replace the y with this notation. F of x is 3x plus 1. So now what you're saying is this side of the equation, which we used to call y, is a function of x. You plug x in, and it will turn this into that value. So with that notation, I could write, well, what's f of 1? What would that be? That means replace your x with 1. And that's multiplication, so you do that before the addition, right? So this would be 4, right? And we keep doing this. F of negative 2, what's that? 3 times negative 2 plus 1, so negative 5. With me? Now, we know that we could graph this, right? We know that this is a line. That means this function is also a line. And these actually correspond to points on the line where we had before the x and the y coordinate. Now we can say it's like x and f of x. Here it would be, what's the input? 1, and what's the output? 4. And then over here we could say -2 and -5, right? And if we start plotting these, we get a line. Now, a function is more general than this. This is a specific example of a function. This is what we call a linear function, because when you graph it, you get a line. But there is no restriction. Does not have to be a line. In other words, you have other functions that if you were to graph them, they are not lines. So let's look at some of those. Let's take a look at another function. I'm going to define it for you. So I'm going to give you this function. Let f of x be defined as x squared minus x minus 6. Now I put let because it's kind of like I'm presenting the function to you. I'm telling you what this machine does. That's what it does. You give it an x, and this is what it does to it. It operates on it. So I would like for us to find the following. Part A. What is f of, we'll make it easy to start, f of 1? -6. So all you're doing is replacing all your x's with 1, right? So 1 squared minus 1 minus 6. This is 1. 1 squared is 1, right? So 1 minus 1 minus 6. And I hope everyone would get -6 there. They put that together. Can someone tell me what that would be as an ordered pair, as a point, if I were going to try and graph this point? What would it be? 1, -6, right? That would be a point that I could put out there if I wanted to. All right, B, let's do f of -1. Be very careful here. I'm going to write it down 2 different ways. One of them is going to be correct, one of them is going to be incorrect. You can tell me which one is correct. Let's see. I'm going to write it down 3 different ways, and you can tell me which one of these is correct. Okay, I've given you 3 choices there. Which of those is the correct way to write it down and the correct result? The last one. Okay, what's wrong with the first one? What's wrong? This right here, right? Right. You take a look at this right here. What that means is you're going to take something, right, x, whatever it is, and you're going to square it. -1 written as this with the squared does not mean -1 times -1. -1 squared means negative times 1 squared. So the squared is only acting on the 1. The negative is like a negative sign out front. That is incorrect. So this person wrote it down wrong. When they squared it, they left it negative, which is wrong too, right? How about this one? They wrote it down wrong, but when they squared it, they actually did it correctly, but that's not right. That's the wrong notation, but luckily got the right answer. This is the right notation, the correct answer. You all understand that? Someone's going to mess that up. Yes?
Isn't it always going to be positive if you have an even notation?
What is what? Is
-1 with the even number notation.
That's a very good question. Can I give you another example right after this?
Sure.
And then we can see?
Sure.
Yes? Because I want to answer you yes, but if I give you another example, then you might be like, Okay, so what would be the ordered pair that would represent this one here? -1, -4? Any questions on that? All right, tell me what this would be. You're going to like this one a lot. See, what's f of -2/3? So help me write it out first. What am I going to put here? Let's use the correct notation. Parenthesis, -2/3, close parenthesis, squared, then minus, parenthesis, -2/3, and then -6. That is the correct notation. What's -2/3 times -2/3? It's -2/3 times -2/3. Is it going to be negative or positive? Positive. And multiplication of fractions straight across. So 4/9 multiply, right? It's all right. 4/9. Those are the types of things that you'll do on a test and not even think about, right? It just happens, and then from then on, it's all out of whack. All right, what comes after this? Minus a negative, which is plus, so plus 2/3, and then -6, and I'm going to write it as 6/1. So I wrote the -6 as 6/1 because I know I'm going to have to add and subtract fractions, which means I need common denominators. And what would the common denominator be here? 9. So you've got to turn all of those things into something over 9. 4/9. How do I do this one? Multiply by 3 on the top and bottom, right? 3 here, 3 here. So what is it? 6/9 plus 6/9. And then I have to do 9 on the top and bottom here. So minus 9 times 6? 54/9. And then you can go straight across. 6 plus 4 is 10. Take away 54. -44/9. That's it. That's the answer. Unless you can simplify that, I don't think anything goes in there. So that's good. So written as an ordered pair, -2/3 and -44/9. So mom was asking, right, whether or not we can always just assume it's going to be positive if you have an even power up there, right? And yes, but just what if I start the problem over and I were to write -x² plus 2? New function, okay? New function. Let me ask you what, that's part A. What would f of -1 be here? That's why I want to show this to you. So what does this -x² mean? It means you're going to square x, okay? You're going to square it first, and then you're going to change the sign of whatever it is. So the proper way to write this would be, okay, I'm going to change the sign of what? Well, what is it that I'm squaring? -1 and then squared, yeah? Now the mistake people will make is they say negative and negative is positive. What's wrong with that? Why can't you do that? You have to square it first. Why do I have to square it first? Order of operations. Exponents comes before multiplication. So I have to actually do this exponent first. Negative times negative would become +1, and then you make it negative. So I still have plus 2 out here. Sorry, I forgot to write that. So this would actually be negative, and this piece right here is 1, and then plus 2, so the answer is 1. See how that, so I didn't want to answer that as, yes, when you see squared, it's always positive, because in this case, it's actually squared, but that negative is going to make it negative. All right, let me give you another example. So a new problem. Let f of x be equal to negative 5x plus 12. Find x if f of x is 17. So notice on every example I've just done, when we were writing like what's f of negative 1, what's f of 2, what's f of this, what's f of negative 2/3, I was always giving you the x, wasn't I? I was always giving you the input, and you were telling me what the output was. What is this giving you? This is giving you the output. It's saying, hey, look, there's an x that I plug in that will give me an output of 17. What's the input? So I'm going to rewrite this equation, but instead of replacing the x with 17, I'm actually going to replace f of x with 17. So I'm going to replace this side, the output side, 17 with negative 5x plus 12. And then I just go about solving the way I did before for x. And what is it? Quickly, I'm not going to work through it. Negative 1. X is negative 1. So if you look at this as a point on the graph, right, or on the graph of this thing, what's the input? Negative 1, and what's the output? 17. So do you see the difference in the wording of the problem here compared to like this? I think it's obvious, right, where the number is? Okay. All right. What if you were to say, let's continue that same problem over there. When is f of x equal to 0? When is the function equal to 0? So what do? Are you plugging 0 in for x? No? No, it says when is the function's value 0? So same thing we did here, right? Except instead of 17, we put 0. And you're solving for x. And again, I'm going to let you work through that. This would come out to be 2/5. Oh, it was 12. I'm sorry. Sorry. I wrote the problem down wrong. This is a 12. My mistake. Okay. 12. When this goes over to the other side, it's negative. And then when you divide by negative, you're going to have negative over negative, which would be positive. So it should turn out to be 12/5. Y'all still good? Okay. All right, now I've shown you that when you have a function, you can have these ordered pairs, right? And we know that if you're graphing a line, those ordered pairs, those points are all going to lie on a straight line. And I said not all functions have to do that. So for this example, what I'm going to do is I'm going to draw you the picture of the function. And then I'm going to ask you some questions. So here's the drawing. This is x. This is the function's value. So instead of using x and y, I'm using x and f of x. And let me just draw a quick function on here. You don't have to be perfect with this, all right? Let's just say 1, 2, 3. So this is negative 3. 1, 2, 3. That's positive 3. That's positive 3. 1, 2, 3. That's negative 3. So here I go with my function. I'm going to start it out, let's say, about right here. Okay, is that a line? I hope that's not a line. It's a couple of different lines, right? It looks like 3 different lines, actually. And in more advanced college algebra class, we call this a piecewise function because it's different lines on different pieces. So over here, it's one line. Between here, here it's different. Here to here, it's something different. 3 different lines pasted together. But here's what I'd like for us to be able to determine. Everyone have kind of a basic idea of this general picture? Let me draw some little mini grid lines. These are just kind of helping you see where these things are. Good enough. Okay, kind of so you can see things. All right, let me ask everyone right now, what's f of 0? So what are you doing to figure out what are you doing to determine the result of this? Yes, well, no, we're not saying where is f of x equals 0. You're saying what does the function spit out if I plug in 0, right? So this is the x coordinate, right? So what is the answer? So I heard some people, what is it? 2. So how are you getting that? What are you doing? Where are you looking? You looking right here? That's 1, 2.
Finding where the x-intercept is, technically.
Okay, so are you looking at this point?
No, I'm looking at 0.
You're looking at an x value of 0. So you're moving along the x-axis until you get to 0, right? Which is right here. And then you're looking up to see, or down to see where the function is. And it's right up here. And so that point right here has the coordinates 0, 2, doesn't it? And that means that the output when you plug in 0 must be 2. Yeah? What about this one? F of 1. So now you're moving, this is the input, right? The x. You're moving along the x direction. You find 1, which is here. And you look up and down to try and find the graph, and it's actually above you, right? This point. And so you look at that point. It has an x coordinate of 1. What's the y coordinate? Looks like 1 again also. Right? So this would be 1. What's f of negative 1? 2. Because you go to negative 1, you look up, right here. That has the coordinates negative 1, 2. What's f of negative 2.057? So you're going to go to your x, right? And you're going to look negative 1, negative 2.05, so just a little bit to the left. Oh, wait, sorry. Let's make that 1. Sorry, 1, 1. I didn't want to go that far out, sorry. Negative 1.057, just a little bit past it, right? Still 2, right? So it didn't matter because this was flat, right? It didn't matter, it's still 2. What would... what's that asking? Yeah, now they're saying, when is the output 0? So you're asking for the x value that gives you an output of 0. So where is the output 0? At where? X is 2. At this point right here, you plug in 2, you get an output of 0. Output 0, input was 2. So it's the x-intercept, isn't it? So here x would be 2. Again, you can see the difference in the notation, right? F of 0, f of 1, f of negative 1, f of negative 1.0, and all of a sudden f of x equals 0. That's what tells you, look, I'm looking for the output. I'm looking for the input, not the output. All right, how about this one? Last one. F. Estimate f of 3. Right, if you know what it is, and this is just too easy, that don't just hold off for a second. I want to call on somebody. Everyone has their name tags. Well, not everyone, but let me see who looks very interested. Bethany looks interested. You always look interested. I don't know why. That's a good thing. So Bethany, when I say f of 3, what are you thinking? No? Okay, is 3 the input or the output? Input, right? So that's the input is always the x. So that means you're going to want to go to the x-axis and you're going to want to go to 3. Okay, so here's your x-axis. Walk along till you get to 3. And now look up or down. Do you see graph above you or below you? Below, okay. Right there, this point. How low is that point? Estimate. Okay, negative 1.5, because you went down. Got it? Okay, I'm gonna stick with you because the last one, you said you had no idea. Now let's see if you have an idea. I'm not picking on you, but this is where you learn. Okay, so. I think it's 2.49. No, I'm just kidding. 2.5, good. See? You understand what's going on here? Everyone got that? Anyone else want me to quiz them? You feel comfortable with that now? Bethany?
Yes.
You feel comfortable with that, right? That's better than not feeling comfortable, right? Okay. Well, that should be enough for you to do the homework over that functions and function notation. I don't think it's going to get any more complicated than that. We have another topic, which we're supposed to start today. And I think it's worth us at least visiting it for a minute. This next topic is actually on our calendar. We're supposed to spend, we're about going to be about a day behind. We're supposed to spend an entire day on this thing, 2 hours or so, on factoring. So I want to get at least one of the factoring things discussed and resolved, and that's GCF, which we've seen before. Do you remember there was one section in the homework about factoring GCF that we did before? There was one on the test. I would say about 70% of you on the test got it right, the GCF problem. Some people forgot to pull the y out on the problem. They pulled like y but not y squared. I'm referring to the test. And then there were some people that really still didn't look like they were comfortable with it. So let's do some GCF factoring. Greatest common factor. This is always the first technique. Always the first technique that we use when we try and factor. There's going to turn out to be several techniques. This is the first one. So for an example, I want us to factor this. 15x squared minus x to the fifth, minus 21x to the fifth. Starting with numbers, can you think of a number that goes into 15 and 21? Yeah. 3, right? So 3 goes into each of these. So you can factor 3 out. Can you think of, well, the common factor is x. You have x squared and x to the fifth. So what's the highest power that they both have? X squared, right? So you can pull an x squared out. And then you have to come up with something in this parenthesis. And can someone tell me how many terms I must have in here? 2. Why? I started with 2, I have to end with 2. And that was another thing on your test. Some of you got caught. There was a -1, I think, that was supposed to be in the middle. 3 terms to start. You should have 3 terms in that parenthesis if you go back and look at your test. So what goes here? 5. So 3 times 5 will give me 15. And then I'll have an x squared. That would give me 15x squared, wouldn't it? And that's what I have. So that's all I need, 5. And then here, what I multiply 3x squared by to get -21x. -7. And how many x's? X to the 3rd. Because when you add this 3 and 2 together, you get 5. So that's GCF. That's the first thing we always do. Now, the new thing today is that after we do GCF, we now have to look at this and see if there's anything else we can do. And it's going to turn out that that might keep going and break down further. It might factor by what's called grouping. It might factor as a trinomial. It might be a difference of squares, a difference of cubes, or sum of cubes. There's all these different things we have to be aware of. And we're going to go through each of those, all right? But I want to start with the first technique being grouping.
Where do you have 2 sets of parentheses?
Yes. So we're going to do that. Okay. So let me do it this way first. That was just one problem for GCF. Now I'm going to move on to factoring by grouping. Does anybody, who's seen grouping before? I know some of you have seen it. What is the key to doing grouping? What do you have to have? How many? 4 terms. 4 terms. You only really look at this method if you have 4 terms. If you have 3 terms, you're not going to be doing grouping. All right? So let's do... Let's do this. Yeah, I want to start off a little easier. Okay, I'll just make it up. X cubed minus 3x squared minus, or we'll make it plus 2x minus 6. I would like for us to factor this. So when we say factoring, factoring means turning addition and subtraction into multiplication. That's factoring. It's the opposite of this. If I told you to multiply this out, right? FOIL that out, you would get x squared minus x minus 6. That's what you would get if you did it and collected like terms together. Going from here to here is called expanding. Going from here to here is called factoring. And we like to be able to factor. It helps us out later when we're trying to build bridges. So, cannot do anything GCF-wise, can you? Is there a GCF? No. How about X? This has X, this has X, this one. That one's missing one. Who cares? Like, can I still pull an X out? You have to have them in all. Okay? You have to have an X in all of them to just be able to pull an X out right now. So there's no X. How about a number? Is there a number that goes in all of these? No. Other than 1, but we never look at that. So we're kind of stuck. All right? So now we move to this grouping technique, and we say to ourselves, all right, do you have 4 terms? Yes, check, we do. And I know there's different ways that people are taught this, all right? So I'm just going to show you the way I do it. What you do is you look at your first 2 terms, and right after the second term, before this sign, whether it be plus or minus, I draw a slash through the problem. That's the way I do it. Now, I completely forget that that's there. I look at just these 2, and I pull a GCF from just those 2, if there is one. So is there a GCF from just those 2? X squared, right? So I'm going to get x squared. I'm going to set up parentheses here. How many terms must I have in here? 2, because I'm looking at 2. I'm pulling something out. I should have 2 here. Which 2 will be in there? Bianca?
It would be x and minus 3.
Good. That's the first part. The second part over here is to do the same process on these two terms. Do you have a GCF in those two terms? Yes. Yes, what is it? 2, right? 2 goes into both of these. So I'm going to leave a little space here. I'm going to put 2. And then I'm going to put how many terms in this parentheses? 2? Yes? Oh, 2. Thank you. And go ahead, since you were raising your hand. What's in there? X minus 3 again. And just do a quick little check. If I distribute that through, I get back this, right? Now, very important step. Was this 2 a positive 2 or a negative 2? It was positive. Please put that plus sign right here. Now, the critical step. We are saying that this line is equal to this line. Now, I know some of you have done this before, right? You just told me you did. So for someone who's done this before, do you want to tell us what I do next? Well, go ahead, Justin.
You combine them, x squared plus 2.
I'm going to write down what you say. X squared plus 2.
And then it'll be x minus 3.
Just right here, like this, like this. This is correct. This is correct. Yeah, that's correct. How many of you would have done it this way? Anyone would have done it that way? What's the difference between this and this? I guess there's a pretty big difference, isn't there? So for those of you who've done grouping before, how many of you are comfortable with this? That you've done. My question to you that have done those of you who've done grouping, why? Why do you do this? What's that?
Because the second one wouldn't come out the same way as that.
These are both the same. You could write this down or this, they're the same answer. Because remember, multiplication, 3 times 2 is the same as 2 times 3, right? Doesn't matter which order. This is multiplication, this is multiplication. So if you flip the order here, it's the same answer. So these two are both correct answers. Most students will tell me it's either this or this, depending on their teacher. My question is why? I don't understand how you got from here to here, and that's what I'm curious.
Foiling it out becomes the original answer.
What, foiling? Oh, if I take this and foil this out, I'm going to get back that original? I agree with you. But why am I allowed to go from here to here? It seems almost magical. Does that not seem magical to you, to do that? I think the reason I'm bringing this up is because most of you are taught to go from here to here, and it's never explained why. Okay? And I think if I show this to you, you'll agree with me that it's pretty simple. Watch. Just free your mind from this problem for a second. Okay. Look at these two things here. What do these both have in common? What does this and this have in you know what? Let me do it this way. Let me do it this way. Squared. This will be much easier for you to see. Let's do it that way. Look at these two terms. You see two terms? Okay, what do these two terms have in common? They both have an M. So if I asked you to pull a GCF, could you? Yes? And you would pull the M, wouldn't you? You'd put an M out here, and then what would you write next? X squared plus 2, in parentheses, right? Because you're supposed to put it back and say two terms in here, and you'd say x squared plus 2, wouldn't you? How many of you are comfortable with that? Yes? That's exactly what you just did right here. So watch this. This is your M, and this is your M, right? They both have it? They both have that, don't they? X squared M plus 2M. X squared M plus 2M. So since they both have an x minus 3, you're pulling the x minus 3 out. And what's left? The x squared plus the 2 in a parentheses, right? That's this version of it right here. And then if you turn it back around, it's this version. So I don't like students that tell me it's this version, because that means that their instructor didn't explain it to them. it means that they just went through like, just do it because it works. Okay, do you follow that at all? I don't know. If you don't, then just remember, this is, you just write down whatever's here, and then you write down the two things, x plus 2 or x squared plus 2 in parentheses, and you're done. Okay? Question?
That's why I got kind of confused, because I thought you would have to do x minus 2 squared, just because it's
Nope.
doable, but that makes no sense.
Nope. It's because you're pulling out a single factor of it. It just sits out there. And so, yeah, if you imagine just taking this whole block of junk and throwing it next to that one and next to that one, you get exactly this. Okay, so the answer is one of these two, all right? And that would be it. So what we'll do is next class, I would not start this homework, okay? Go do those word problems, and you can do the word problems from lines with mixtures and all that stuff. You can do that. You can do the homework for functions. Just do not do the homework for factoring polynomial expressions. We will hit factoring really hard next time, which is tomorrow. If anyone has any questions about their exam or grade or anything like that, you can stay after and we can chat.